J. Bellamy. And this painting, if you look at this part where there should be the signature of the artist, this is actually the objective function of GAN. So this painting was about to be auctioned in USA for a price of US dollar 4,32,500. So let's see. So what is the crux idea? You see, you show GAN images of a particular kind or images from a few classes. GAN can generate similar artificial but very realistic images, similar in class but not exact carbon copy, with certain changes. Something new will be there inside the images, but they will belong to these classes which have been shown to GAN. Such synthesis of new images is an extremely important step in artificial intelligence. So instead of just classical search or classification or optimization, now we were in a state where the computer could actually synthesize artificial image, nowadays also artificial voice signal, artificial text, fake videos. Everything could be synthesized. Like all other paradigms of science, they have good and bad both sides. But first, let me just discuss it. I have skipped some slides so that I can just come to here. GAN uses an indirect training procedure, and if you look at it, the GAN system, GAN comprises of two separate neural networks which has certain communication among them. One of these neural networks is called a generator, which you can see here. The generator network accepts random vectors sampled from some stray multivariate distribution as its input, and they provide pictures or images of certain designated size as their output. So they convert, their input are vectors, which we also called code book vector or noise vectors in GAN literature, and their outputs are images. So by now you should note that the deconvolutional network I talked about a few slides back, or the convolutional net with its flow reversed, can serve as a generator. So the generator initially takes up random vectors from a Gaussian distribution or from a uniform multivariate distribution as its input and provides images as its output. On the other hand, GAN has another neural network that is called a discriminator. The discriminator neural network has access to the externally supplied images of some specific type. These are also called the training images. Okay, so the discriminator network takes an image as its input, just like a convolutional net, and it provides an output which is a continuous number between 0 and 1. We call it a score. It's very simple. You don't have to just do the soft maxing at the output, so you get a continuous output. So this continuous output between 0 and 1, usually if the discriminator is trained in such a manner, if a very bad picture comes at its input which does not match its characteristics to the real world images of some specific kind, then the discriminator assigns it a very low score of near 0 and stamps it as fake image. Otherwise, the discriminator stamps it as a real image. If it is very good, matching with the real world images, then it's a real image. So the generator generated images can also be fed into the discriminator. These two neural networks, actually, when the GAN is being trained, these two neural networks compete with each other in an adversarial framework. So the generator generates, this is the story, try to understand. The generator generates fake images. These fake images are fed into the discriminator. The discriminator already has experience of how the real world images should look like. So the discriminator assigns a score to the generated image based on its quality. Initially, the generator has all random weights and biases. So it will generate very poor quality images. and the discriminator will assign almost zero score to all of them. But gradually the generator learns as its weights and biases are updated. The generator learns to generate more realistic fake images, and the generator tries to fool the discriminator. It tries in such a way that the discriminator may assign high score to the generated images, assuming them to be real. On the other hand, the discriminator enhances its capability to make finer distinctions between the images coming from the generator and the images coming from the real world training set. This way, both the neural networks, improve each other. Goodfellow used a very nice analogy in one of his articles, I think in Communications of the ACM. So he said, the generator and the discriminator setup is like a team of criminals who publish fake currency notes and the police team who are in charge of catching up such scams. So the fake currency providers publish fake currency notes, and initially they were very inexperienced, not that experienced. So of course there will be a lot of inaccuracies. The Gandhi's diagram, the face of Mahatma Gandhiji will not be perfect. The Ashok Chakra will not be perfect. The signature of the RBI governor will not be in place. So the police will very soon catch it up. But gradually, as time proceeds, so the police will put them in jail, and while in jail is the best university for criminals. So while in jail, they will learn how to publish very realistic fake currency notes. So when they are out on bail, they will try their second hand on publishing realistic fake currency notes, and they can really fool the policeman. But finally, getting a lot of complaints of fake notes, the police will also increase their expertise. They will have certain chemical test procedures and catch up the criminal team again. And this goes on and on. Both of them increase their efficiency. Same is the story with GAN. So if you look at the generator in detail, what is happening inside is the generator. Generator accepts such code vectors and creates such images from the code vectors. Initially, as I said, the code vectors are all coming from, code vectors are very small dimensional. They may have 10 dimension, 50 dimension, 100 dimension. They are sampled from a latent space. Initially, the latent space has no meaning. Through the training of the generator is actually imposing certain meanings to different points of this latent space. So these vectors, maybe 100-dimensional vectors are being sampled, and the generator is somehow creating an image of maybe 64 cross 64 or 128 cross 128 images are being created by the generator. And so these are the images and these are the related code vectors. The generator is trying to relate certain code vectors with certain images from a latent space. Initially, the code vectors just are sampled from a random distribution. So the neural network generator tries to create an image which should be very close to an actual image, as close as possible. On the other hand, this is in stark difference from neural network classifier. The neural network takes an image and creates a one hot vector which should be very close to the actual class encoded one hot vector. Like if this is a 1, then at the output, the 1 entry should be marked as a real one and all other entries should be 0. So this is the difference between generator and classifier. Okay? The discriminator, on the other hand, maps an image into a real number score. Its input is an image and its output is a real number score. If the image is good enough, realistic, then the score will be very close to 1, otherwise very close to 0. So the discriminator is also called evaluation function, potential function, etc. Can we use the guideline from the discriminator to generate the objects? The answer is yes. The discriminator provides a score. That score is used to generate the objects. So the general algorithm for discriminator training is that given a set of positive examples, who are these positive examples? These are the training images, the training data supplied from outside. The discriminator generates a set of negative examples like this. Where from it gets these negative examples? Very simple. It can use a generator to generate negative examples. Okay. So in each iteration, the generator initially, once again, the generator is initially untrained. So it will generate only certain host-like images like this. It's like you have a kid who doesn't know anything about drawing. You give the kid a pen and paper and ask her to draw. So she draws certain zigzag patterns. You don't expect her to draw a real, very good looking painting at the first go. That happens with the generator. Now you as a parent, you will provide certain guideline to your children, your child, or you will put her in a drawing school. Thereafter, she learns to draw meaningful things, right? So here, initially the discriminator's job is to differentiate between real images and such bad fake images. So that in each iteration, the discriminator is trained similar to a two-class classifier. One class is for real image and the other class is for fake image. Fake images come from where? Fake images come from generator. Okay. And the generator, usually what we can do is we can make the generator generate a number of fake images, of which we will choose only those which have maximum score from the discriminator. You see, initially, all the scores will be like 0, 0 0.1, 0. 0.12, 0.05, very low, close to 0, because all the images are very bad looking. So out of them, we can pick up the highest scores given by the discriminator, even if they are very close to 0, and we can set that as our example of negative, the fake images. Okay. So the generator generates certain extilts, and these extilts are such that they may extract maximum score from the discriminator. Such images are used as the negative examples for the discriminator training. So the neural network generator receives codes. From the code, it creates an image, and the image goes into the discriminator. The discriminator assigns very poor score to that. This image is in the hidden layer. And then the generator, based on that feedback from the discriminator, the generator weights are updated. New images are created while the discriminator remains fixed until the generator can extract very good score from the discriminator. It's like the discriminator is like the teacher and the generator is like the student. The student writes answers to certain descriptive questions in literature-like subjects. The teacher, which has certain subjective judgments, the teacher is not very happy with the linguistic quality. So the teacher assigns 3.5 out of 10. So the student once again rewrites that. This time the student uses many ornamental phrase, idioms, etc. Nice English. So the teacher updates the grade to 6.5. This goes on. Okay. Similar thing happens between the discriminator and the generator. So let's put things together. These are the components. This is giving you some conceptual idea about GAN should be trained. Now let's look into the real training process of GAN. So we initialize the generator and the discriminator neural networks with random weights and biases. The weights of the generator are denoted by G and the weights of the discriminator are denoted by D. So in each training iteration, we sample some real objects like this. The generator generates some fake objects like this. And then the real objects are marked with 1, fake objects are marked with 0. The discriminator is trained on this training set. You know, for the training set, it must have the training label. So the training label for real images from the training set is actual big training set, where from we just, suppose we have 500 images in the actual training set and we use only batch of 10 images or 15 images. and we generate 15 more images from the generator as our negative examples. So the negative examples are stamped as 0 and the positive examples are stamped as 1. Based on this new small batch of training data, the discriminator weights are updated. Then the discriminator is fixed. Now the discriminator has already learned something, it is fixed. Now what happens? Now the generator generates a number of images. Based on the feedback from the discriminator, the generator weights are updated. Until the generator is generating very good images, which could get almost 1 score from the discriminator. Thereafter, this updated generator is used to generate negative examples for the discriminator. That means so that now the discriminator should be able to discriminate, differentiate between the generated and real images up to a finer extent. It learns a finer level of distinction between these two images. That is asserted. That's why this improved generator is used. So the improved generator generates improved images, which are again labeled as 0. Then the discriminator is updated. Then this updated discriminator is used to update the generator, and these two goes on. The first part is learning of the discriminator, and the second part is learning of the generator. These two parts go hand in hand. So the benefit of GAN, from the discriminator point of view, we can use the generator to generate negative examples. We don't require anything else. And we are using those negative examples for which the discriminator provides maximum score. From the generator's point of view, we still generate the object component by component, but it is learned from discriminator with a global view. So we get a global quality assessment of the images generated from the generator. Now we say, from the language of game theory, we say the generator and the discriminator, as I said, they are kind of in a tug of war. We say they are playing a two-player zero-sum game. What is that? Two-player zero-sum game means that the sum of total profit is always 0. If one player wins by +5, the other player will lose by -5. Why is it so? First of all, let me tell you, don't be frightened by looking at this sort of mathematical expressions. Every neural network is trained ultimately by using the gradients of some objective function. Okay, you will have an objective function, you will calculate the gradients of the objective function, and by using such gradients, you will update the weights and biases of your neural network. That's a standard practice. Weights and biases are updated by using the gradients in a back propagation manner. Deep generative adversarial networks. Generative adversarial architectures may be deep or may be shallow. Usually we use deep convolutional architectures, especially when we want to generate high resolution images. The codes are very easy. Lots of Python implementations are available all over internet. But it is important in this talk to understand this objective function also. It is called a minimax objective function. What is it doing? Let us suppose theta g is the set of parameters of the generated network, and theta d is the set of parameters of the discriminated network. All weights and biases of the generator denoted together as theta g, for the discriminator denoted together as theta d. Okay. Now, this E stands for expectation. Expectation will be represented nothing more as an average. So we pick up, let's say, a small batch of training examples. These training examples are supposed to come from the real data generating distribution. The real data has the distribution denoted by P data. X tilde P data means this X is an image coming from the real training set. X is sampled from the original data distribution. Now, capital D of X is the current discriminator score provided to this real image. Log of that is a logarithmic version of the score. And expectation of that is nothing but the average logarithmic score provided to images sampled from real data. Got it? Then look at the second term. Z is a codebook vector generated from some stray distribution, as I said. G of Z is an image generated by the generator when it receives Z as its input. D of G of Z is the feedback or score provided to that image by a discriminator. 1 minus D of G of Z is the inverse of that score, and log of 1 minus D of G of Z is basically the logarithm of that inverse score. E once again stands for expectation, which is nothing more than averaging, because we are dealing with finite number of examples only. So the discriminator, so this part is the discriminator output for real data X. Discriminator gives it its score, and this part is the discriminator output for generated fake data GZ. Now you think what should be done by the discriminator? The discriminator should want to maximize the objective, because it should want that when X comes from a real data, dx should tend to 1. That means log of dx should tend to 0. Otherwise, log of dx, if dx is, let's say, 0.5 or 0.2, log of dx is negative. So discriminator tries to maximize the first term. Also, discriminator tries to catch up the fake images generated by the generator by assigning G of Z a very small score. That means D of G of Z should be very small. That means 1 minus D of G of Z should be large. So from the discriminator's perspective, both of these terms must be maximized. So it's a maximization problem. On the other hand, the generator has nothing to do with the first term, because note that the generator doesn't have access to the real data set, to the training data. So the generator attacks only the second term. And the generator tries to generate so wonderful images such that G of Z should be extremely good. That means D of G of Z should be close to 1. That means log of D of 1 minus D of G of Z should be very small, because D of G of Z is very close to 1. So the generator wants to minimize the objective such that D of G of Z is close to 1. And the discriminator is fooled into thinking that the generated GZ is real. So it's a minimization problem from the perspective of the generator. Okay, that's why we call it a minimax objective function. This same objective function is used for the training of both of them. What we do is we do a gradient ascent on the discriminator. We could do while we fix the generator weights and biases are clamped to certain values, and the discriminator is updated through gradient ascent. This is nothing but gradient descent, but with a negative sign. We do not follow the negative gradient direction because we want to maximize. So we want to climb uphill. That is the gradient ascent. On the other hand, the generator objective is minimized by using a gradient descent. But there is a problem. If you look at this curve, which plots log of 1 minus x versus x, the curve has a large flat portion, especially when it is very small. Very small means what? Log of 1 minus d of g of z, very small means d of g of z is big. So, you see, we want to train the generator, right? So, this portion, 1 minus d of g of z is small. Log of 1, sorry, d of g of z is small. That means the discriminator is triumphing over the generator. D of g of z should have been bigger. So now we need to carefully tune the weights and biases of the generator network. But when d of g of z is small, 0.2, 0.4, etc., in this portion, the graph is quite flat. What does that mean? Flat curve. That means that if you try to draw tangents, the tangents will have their slopes close to 0. That means we are going to face the vanishing gradient problem. If the gradients are very small, components of the gradient vectors are very small, That means the updates of the weights will be very, very slow, right? So in order to alleviate that, when we require good updates in the weights, we have very small gradients. So to avoid that problem, a very simple trick is to, instead of minimizing this log of 1 minus d of g of z, we could simply maximize log of d of g of z. Same thing. Minimizing 1 minus x is equivalent to maximizing x. So following that, we use this sort of, okay. Yeah. So now what, instead of this, what we could do is, we could maximize this log of d of g of z. That means we could also use a gradient ascent on the generator. Now you see, in that case, our objective function looks like this one, this green one. And if you look at the green one, it's actually the negative because we are now maximizing. It has a quite good change of slope in this portion where the signal requires, the generator really requires updates. We call it a high gradient signal. High gradient signal is very important because it can give us meaningful large updates of the weights and biases. Okay. So putting everything together, this is the GAN training algorithm as has been taken from this original paper. For number of training iterations in case states, we sample M noise samples. That means we will create M images from the generator. We sample M examples from the data generating distribution. That means very simply, we take M training examples. We update the discriminator by ascending its stochastic gradient like this. So you see, all the training steps that I have discussed earlier are summarized through this adjustment of the weights and biases of the two neural networks. So we update the discriminator network by ascending its stochastic gradient. So we take, now you see the expectation operator has been replaced by the sum divided by m. So 1 upon m times sum over this loss for m training examples. This is the average. So this is the average loss. And we take a gradient on this average loss. This is a cross entropy type loss, if you have heard of that. Otherwise, just looking at this is fine. Similarly, for the generator, so once this training is over, this for loop has ended, we go to the generator training. And in the generator training, we keep the discriminator fixed. And then we update this objective function, average of this objective function over m fake images generated by the generator. This goes together. 3 different scenarios can appear during the training of the GAN. One is a real world image comes to the discriminator says it is fake. So now the error function behaves in such a way that the discriminator weights are updated. Now the discriminator is doing bad things, so it requires some punishment. The generator generates a fake image, the discriminator gives it a very low score. That's a true negative scenario. So the generator has not been able to successfully fool the discriminator. So now the generator requires update. And the third scenario is the false positive scenario. The generator generates a fake image, the discriminator says it is real. So now the discriminator requires update because the discriminator is not able to catch up the generator. It was overwhelmed by the image generated by the generator. So these are the 3 situations that can happen. I have already discussed these things.
Meeting
training cycle modes I have also discussed. So the process of once the generator is updated, then the other time the distributor is updated, this process continues until the generated distribution, that means the data generated by the generator, is almost indistinguishable from the true distribution. And we say the networks have reached a state of Nash equilibrium. That's a game theoretic equilibrium condition after the famous economist and game theorist mathematician John Nash. So until it reaches the condition of Nash equilibrium, I will try to relate it a little bit here. So this is a simple illustration which shows you have a two-dimensional distribution. The target distribution is circular. You can see the blue dots on the circle. And the generated data is this orange dots. We see how gradually the generated data captures and assumes the target data distribution. This is a simple, illustration, and we can see GANs have, quite fast adaptation to the target distribution as compared to the variational autoencoders. But GANs are not meant for such easy two-dimensional point generation. So if you look at these images, what do you see? GANs were trained with images of horses, sofa sets, buses, churches, and so on. And thereafter, GANs generated its own horse images, own sofa set images, own buses, own churches, none of which exist in practice. Try to understand. None of them exist in practice. This is how the GAN images evolved with time. In 2014, we didn't have enough GPUs. Now we have a lot of tensor processing units, and parallel computing architecture has flourished like anything with the growth of NVIDIA. So in 2017, if you look at this image, GAN was trained with Hollywood celebrity images like Tom Hanks, Tom Cruise, Brad Pitt, Angelina Jolie, and so on. You can name a few more. So after such training, GAN generated its own celebrity face. So this person doesn't exist in practice. Although you look at the camera clipped image of this person. This lady, you can see her wrinkles in the eye, these gray hairs, and all the details. But this lady doesn't exist in practice. So you see the danger. GAN can generate a high resolution photographed image of a person who does not exist. Am I clear? Similarly, not only human faces, the recent Big GAN project by Google DeepMind shows that GAN can generate images from classes of ImageNet, 1,000+ classes, and with better than before quality. So all these images are fake actually. They were not photographed. Sorry, they were never really photographed. But if you look at them, they appear to be so realistic. The GAN research is almost at its peak. A new generative adversarial network architecture for different purposes are coming almost every week. There is a GitHub repository called GAN-Zoo, which keeps track of all these new developments. Now, nothing in machine learning comes as a free lunch. There is a principle of no free lunch in machine learning. Am I clearly audible to all of you till now?
Yes, sir.
Yes, sir.
Okay, very good. So nothing in machine learning comes without a price. In case of GAN also, I told you, basically like all other generative models, GANs try to, estimate the underlying probability distribution of high dimensional objects, like a speech signal, a text document, etc., etc. Now, it is basically, you can view GAN as a density estimate. Literally, it is a density estimate. And since it is a density estimator, it is not straightforward to compute the density expression P of X. The density function, nature of the density function in such a high dimensional space cannot be appropriately judged. We see that they are very good at sampling and generation, but the generation appears mostly like through intelligent interpolation. The GAN training is very hard, sometimes because of non-convergence. Most often the discriminator can win over the generator, and if that happens, then the generative process is not very good. Discriminator winning over generator means the discriminator is always able to catch up fake images. That means the generated images are not of very high quality. If that happens, that is very bad actually. Another very big problem with GAN is the mode collapse problem. Later on, lots of GAN architectures and advanced literature have been proposed to avoid such problems. What is this mode collapse? We will see a few of these issues and then I will open for question answer. Okay. So maybe I have time until 4 o'clock. So just, you see, deep learning models usually involve a single entity or a single player, like the convolutional, only one convolutional net. The player tries to maximize its reward or minimize its loss, uses SGD with back propagation to find the optimal parameters. SGD is called the stochastic gradient descent. SGD under certain conditions can guaranteedly converge, but since the objective function of this sort of convolutional neural networks are highly non-convex, you can end up with a local minimum. That's a big problem. On the other hand, GAN involves two such players. That means two neural networks. The discriminator is trying to maximize its reward. That means trying to maximize that function. That function I have shown to you as a cross entropy loss. You can call it a reward function of the two-player game. On the other hand, the generator is trying to minimize the same function. That means the generator is trying to minimize the discriminator's reward. We can look at it like that. SGD was not designed to find out the Nash equilibrium of a game. It's a game theoretic setup. So we might not converge to the Nash equilibrium at all. That is the problem. Nash equilibrium, GAN is based on the zero-sum non-cooperative game. Non-cooperative means competitive. If one wins, the other loses. That means between the discriminator and the generator. If the generator generates beautiful images, then the discriminator should not be able to tell them apart from the real images. Okay? So the discriminator has to lose. Discriminator has to lose. It should be defeated. It cannot so happen that both of them wins the game. So your opponent wants to maximize its actions and your actions are to minimize them. In game theory, the GAN model converges when the discriminator and the generator reach a Nash equilibrium. And that is an optimal point for the min-max equation below. So at that, beyond that point, no further minimization or no further maximization is possible. Since both sides want to, undermine the other, say Nash equilibrium happens when one player will not change its action, regardless of what the opponent may do. This is very important and I don't think you will understand it easily, but the Nash equilibrium is a very important condition related to GAN. Qualitatively, it says both the players want to undermine the others, right? So a Nash equilibrium will occur when one player will not change its action, regardless of whatever the opponent may do. Then we say, okay, the game has come to a Nash equilibrium and more than this is not possible. Consider two players A and B which control the value of X and Y. Suppose X, this function, this is same as a function like this, but we take a very easy function just to illustrate this point. Suppose this function V of X comma Y is XY. So initially, and this function must be minimized for X, maximized for Y. State 1 is this, X is greater than 0, Y is greater than 0, V is greater than 0. What could be the strategy for these two players? Now, this is a very simple game, so the players have only one strategy. What could be the strategy? Since X wants to minimize, so X will reduce itself, Y will increase itself. So in the next state, it can so happen that X has become negative, Y is still positive, and V is negative. Now, V is negative. Try to understand. Now, Y wants to maximize the V. So Y will have to reduce itself because V has now become negative, and X will further reduce itself. So it could so happen that now Y has become less than 0, X has become less than 0, and V has become positive. So in the next state, X greater than 0, X tries to increase itself, Y also tries to increase itself. So this goes on until we reach state 1 once again. So this is an oscillation scenario. You see non-convergence. We again get back to state 1. The Nash equilibrium of this simple game is X equal to Y equal to 0 and V equal to 0. This is the only state where whatever Y does, Y increases itself to 10, decreases itself to minus 20, doesn't matter until and unless X keeps on 0. Is that clear? So it is the only state that any opponent's action will not change the game outcome. That is the Nash equilibrium of this game. And what I have illustrated here is simply how oscillation sets in. So if we try to use gradient descent, we could not do that. In fact, the signal goes on, the X and Y updates go on oscillating like this. If we plot X, Y, and XY against the training iterations, we realize our solutions do not converge. The second, so this non-convergence is a big issue during GAN's training. Another big issue is the mode collapse. The generator may fail to output diverse samples. If the target is like this, expected outcome is like this. So generate the distribution same as the target. But the output, final output could be like this. So this says mode collapse, if this is from the probability density viewpoint, mode collapse is like this, that the generator generates a very good image at some point of time, and the generator shows that image to the discriminator. The discriminator is very pleased with the image, gives it a very high score. But then the generator goes on generating the same image again, and again. Because, and the discriminator also falls in a loop. The generator neglects other types of images. If you look at the MNIST data set, in MNIST data set, we say there are 10 modes because it is a collection of handwritten digits from 0 to 9. And initially, this was the situation. So real life data distributions are multimodal. Multimodal means within the same data, there are multiple internal classes. MNIST has 10 major modes from digit 0 to digit 9. So if we use two different GANs, the top row produces all 10 modes and the second row produces only a single mode, you can see. And if we go gradually to further approaches, maybe all the modes collapse to only a single one. This is the mode collapse problem. And mode collapse is a very difficult problem actually. It happens most often while the training of GAN doesn't converge. So this is another very big issue. Now I will gradually go towards the concluding part because I don't know, I mean, the other applications and other things we will discuss later. So GAN has been used tremendously. Let me just reshare. Yeah, GAN has been used tremendously in several very interesting applications. I will show some of these applications later, but for now, Cycle GAN was a 2017 paper in the famous ICCV conference, the International Conference on Computer Vision. If you look at this paper, you see it handles the style transfer problem with GAN. So Cycle GAN was trained with the images drawn by famous artists like Monet, Van Gogh, Cézanne, Ukiyo, and so on. Now, if a photograph is given as input to Cycle GAN, it can transfer the brush stroke styles of these famous artists into the photograph. It can convert a Monet's photograph into a photo and vice versa. It can convert a zebra into horse. It can convert a summer landscape into a winter landscape. Now the same thing is happening for voice conversion also. So in my recorded voice, it can incorporate the voice texture of Mr. Amitabh Bachchan. So Bachchanji's that high buzz voice, so mesmerizing voice, and in that voice, this deep learning lecture is delivered to you. Just think of it. So style transfer means while preserving the content of the image, a different style could be merged with the image. Similarly, GAN found several backend applications like the neural photo editor, where it's a behavioral photo editor. You can extend the hairband as you wish by taking the cursor. You can make different colors. It matches with the cut of the face and so on. Similarly, pix to pix, an image to image translation that often gets quoted in cross-domain GAN. So you provide this input of an aerial image, it creates a map. You give a sketch image, it can create an output. Now, pix to pix is quite old, 2018, 3 years old. Now, this has come into text to image, image to text, voice to image. So your little baby, there is a computer application and your little kid is saying, the tiger is coming with from a bush, okay, or there is a nice nightingale bird on the branch of a tree. So having said this, immediately on the computer, this image is drawn and it is displayed. So the computer can interact with the baby in that way. That it is converting a voice to image. Initially it was image to image, then text to image, image to text. Now it is voice to image, voice to voice. All the cross-domain conversions are possible by using the same. I will show you the internal, structure of the cycle GAN. But in such GANs, usually they use 2 different generators or 3 different generator, 1 discriminator, 2 discriminators, or 1 classifier discriminator generator. Such 3-4 player architectures are the variations of the original GAN architecture, which can get us to such nice cross-domain transfers. You can see this is another fun application where you provide a input expression, and then it can create a video by telling you how Mona Lisa looks like if she imitates your input expression. So I think with this, I should stop. Let me remind you once again, Geoffrey Everest Hinton, you can see his face here. He was actually the inventor of the famous backpropagation algorithm long back in 1986. And since then, he is saying that hidden layers in a neural network can create magic. The rest of the world took almost 20 years or more to understand what he was saying. He is called as the godfather of deep learning. With so much developments with backpropagation and deep learning and other machine learning, neurosciences, Hinton still believes that we are light years away from actually understanding how human brain behaves. So he remarks, the future depends on some graduate student who is deeply suspicious of everything I have said. That's why keep on doubting. Probably from your questions and doubts, new areas can emerge. I would like to acknowledge a number of resources I have used in these slides, especially the tutorial talk by Hyung-Hee Lee from National Taiwan University. These tutorials are all freely available. The deep learning book by Ian Goodfellow, Benjiu, and Corvin. This book is in fact all the top conference papers, AAI, New Reaps, ICML, the biggest journal of machine learning research. All such books and tutorials in machine learning are available free of subscription. You don't need to pay a penny to any big publication house like IEEE, Springer, or anywhere. You get an internet connection and you get all of these things. So that's how this deep learning book is also freely available. Roger Gross's CycleGAN, ConvNet slides from Abin Rusgard, and so on. So all these resources are very useful. You can have an individual look at them. So with this, I would like to, close this session, and maybe we can take up a few questions if you have. Okay. Any question from your side? Hello, am I audible? Any question?
Yes,
Yeah. Okay. Okay.
Any queries, please? Okay, sir. I want to give you vote of thanks. On behalf of RGPV, I extend a really hearty vote of thanks to our expert, Professor Swagatam Das, sir, who spared time from his busy schedule to grace the occasion. Today, we had an opportunity to hear your thoughts on tiny differences between machine learning and deep learning, predictive and generative models, GAN, discriminator, GAN developments, problems with GAN, cycle GAN, and all. This will surely be going to encourage us in our future events and research. Thank you so much. We are very thankful for you, sir. Thank you so much.
Thank you. Thank you.
Thank you, sir.
Thank you. Have a good day, all. Best wishes.
Thank you, sir. नेट चला क्या तुम्हारी? फोन लगा के पूछा था क्या उनसे? फोन लगाया उधर? नहीं चल रहा, बोला कि आज इसमें ये गाइड देखो यहाँ पे स्पीकर वॉइस प्रकाश कराना और यहाँ मान के रखो कौन सा माइक्रोफोन।
चलिए, I think all of you submitted the session feedback, no? Now, so can I end the meeting? We'll meet in tomorrow first session at 10 o'clock. Okay, I am ending the meeting. We'll meet in the at 10 o'clock.
Thank you, sir.
tomorrow. Okay. Thank you. Please remove all of you from the meeting, please. Kindly remove yourself from the meeting.